So, we said that the second law of thermodynamics says that the entropy of the universe is maximized at equilibrium. So during a spontaneous process, so things that have a natural tendency to occur are associated with an increase in the entropy of the universe. And in the previous slides, we talked about practical ways of we look at it from a practical point of view where we can calculate changes in S in terms of heat measurements, right? So the question is, what is entropy really? We just defined it, right? But what is it in terms of, let's try to get a feel for what it is at the molecular level. Well, first of all, let's take a look at the statistical definition of entropy, okay? Entropy it can be defined as a measure of the number of ways that something can exist or happen, okay? So let's consider a two-die toss. You know what a die looks like? Yeah, 1, a 2, and a 3, and so on, right? It's got 6 faces. So how many ways can you come up with a pair of snake eyes? If you toss a die, pair of dice. One way. They both turn out 1, right? 1 and 1. So you can get 2, right? So if your outcome is 2, let me tabulate it here. Let's look at the possible outcomes of a two-die toss. Number of ways you can get a 2 is how many? There's only one way.
Yeah.
How many ways will they add up to 2? One way. They both come up 1. Right? 1 plus 1 is 2. How many ways can your toss come out, give you a total of 3? So you can have a 1 and a 2. Or this one could be the 2 and the other one could be the 1. So 2 ways, right? You can either have 1 plus 2 or 2 plus 1. It will give you an outcome of 3. How many ways can you come up with a 4? 3 ways. What are those 3 ways? 2 and 2, 2 plus 2, or you can do 1 plus 3 and 3 plus 1, right? Okay. How many ways can you come up with a 5? See the pattern here? So it's 1 plus 4 or 4 plus 1 or 2 plus 3 or 3 plus 2. How many ways can you come up with a 6? 5 ways? Okay. How many ways can you come up with a 7? 6 ways? How many ways can you, what are those 6 ways? 1 plus 6, 6 plus 1, 2 plus 4, 4 plus 2, I forgot the 5. 2 plus 5, 5 plus 2, what else? 3 plus 4, 4 plus 3. So that's 6 ways, right? How about an 8? 7 ways? What are those 7 ways? Tell me. How do you come up with an 8? 6 plus 2, 2 plus 6, 3 plus 5, 5 plus 3, 4 plus 4. There is no 1 plus 7, and there is no 7 plus 1. Right? So it's not 7 ways, it's only 5 ways. How about a 9? 4 ways. A 10 would be 3 ways. So why do you think it's called lucky 7? That's the most probable outcome, right? Everything's random, right? So we say then an outcome of 7 would be a high entropy condition. It's the outcome that has more ways of showing up, okay? So that would be a statistical interpretation of entropy. So the outcome that has the highest probability is a 7. That's the one we say, and that has the highest entropy. So entropy then we say is a measure of the number of ways something can happen. And when we're applying the concept of entropy to the way energies are distributed among the molecules, it turns out you get these high entropy conditions become overwhelmingly favored. Okay, and so that's the way we explain natural tendency for entropy maximization. The natural tendency for entropy to be maximized, as stated in the second law. It's all a question. It's all a matter of probability. And once we apply these ideas to atoms and molecules, it turns out that the high entropy conditions in these cases are overwhelming. You have overwhelmingly more likely to occur. Okay, so let's apply then this idea to molecules and atoms. Entropy is really, okay, for the most part, it's a measure of the number of ways of distributing the thermal energy among the atoms of a system. Okay, so it's a measure of the number of ways. So if W is the number of ways, then the entropy can be defined as directly proportional to the natural log of W, where this proportionality constant K here is known as Boltzmann's constant. So the more ways you can distribute energy, the thermal energy among the atoms of a system, then the higher the entropy. That is why when you increase the energy, okay, there would be more ways of distributing it, as we shall see in a little while. Okay, so what happens if all of the atoms are at their lowest possible energy? So they don't have any thermal energy. Okay, zero thermal energy. All of their energies, you can say, is potential. What would be the number of ways you can distribute nothing? If I've got $0, how many ways can I distribute $0 among all of you atoms in this classroom? One way. You all get nothing. That's the only way, right? So number of ways of distributing nothing is one way. What's the natural log of 1? 0. That's why it's convenient to define the entropy at absolute 0, where you don't have any thermal energy to distribute, to be 0. Okay, so entropy is 0, and there's only one way of doing things. All right. So what are the factors then that affect entropy? We said when you heat something up, the entropy increases, right? Well, if you have more thermal energies, then there's more ways of distributing the thermal energy. That means a higher entropy. Let's look at an analogy to make this easier to grasp. If I have, let's say energy is money, okay? Let's say I'm distributing energy, so I'm distributing money. So I'm going to distribute nickels between two people. Okay, so Michelle and Jessica. Okay, so I've got 3 nickels to distribute between you two. Okay, first of all, I have 2 nickels, 3 versus 2 nickels. If I have 2 nickels to distribute between you two, okay, so I have Michelle and Jessica, all right? How many ways can I distribute 2 nickels between you two? Okay, you each get 1, or Michelle gets 2, Jessica gets none, or Michelle gets none and Jessica gets 2. That's 3 ways, right? Or what if I have 3 nickels? I can give Michelle 3 and Jessica none. I can do 2 and 1. I can do 1 and 2. I can do 0 and 3, right? So there's more ways. And you can see if I even have more nickels, I'd have more ways of distributing them between you two. All right? So increased thermal energy leads to an increase in entropy. Okay? Now, the other factor is quantization of energy. You've learned in Chem 105 that energy is quantized, right? Atoms and molecules can only have certain allowed energies. They're not going to just have any amount of energy. Okay, there's restrictions on how much they can have. It's like saying, okay, for our analogy now, we're going to be picky. We're going to say Michelle is picky. She's only going to accept pennies. She's not, okay? And so let's say Michelle and Jessica are picky. They're only going to accept pennies. Or no, they're not picky. They'll accept pennies. So And let's see, Augustine and what's your name back there? Kelly and Augustine are picky. They'll only take nickels. Okay, so quantization, so pennies versus nickels. So I can't give you anything other than 5 cents or 10 cents, right, Kelly? And Jessica and Michelle, I can give them pennies. Okay, same thing. I have 10 pennies versus 2 nickels. That's 10 cents either way, right? How many ways can I distribute 10 pennies between 2 people? So Jessica and Michelle again, 10 pennies. 10 and 0. Well, 10 and 0. Or I can give you 9 and Jessica gets 1. I can give you 8, Jessica gets 2, and so on. Right? It's a lot of ways. Between Augustine and Kelly, I only have 2 nickels. So 10 cents versus no cent, right? 5 cents versus and 5 cents, right? And 0 cents and 10 cents. Fewer ways. So the bigger the gaps between the allowed energy levels, the fewer ways you can distribute the thermal energy. So the bigger the gaps, that means they're more picky in terms of how much energy they can accept. So that factors into the amount of entropy the system can have. Okay? So in general, this is one thing you'll find in quantum mechanics, the more freedom of movement the atoms have, okay? We associate that with the notion of disorder. The more freedom of movement atoms have, the closer their energy spacings and the higher the entropy is, okay? So you can see this one right here, the 2 people who would accept pennies versus the 2 people who would only accept nickels, you get a higher entropy for the people who would accept pennies. Okay? So the closer the energy, the more the freedom of movement, the closer the energy spacing. So let's look at examples of that. Predicting delta S. Okay? Let's say you are to heat a sample. Okay, what did we say happens to the entropy? Increases, right? And that's because at a higher temperature, you have more thermal energy. That's higher entropy. We already talked about that. What about if you're expanding at constant temperature and pressure? Okay? What happens if something expands? Let's just say constant temperature. Okay? So let's say I have, for example, a gas in here. Okay? And I were to open up this box right here. What happens to my gas? It spreads out, right? It fills the entire container. By increasing the volume, what am I doing? I'm giving my molecules more freedom of movement, okay? So the allowed energies that they can have, the spacings between the allowed energies they can have get smaller. Okay, so we say the quantization of energy gets smaller. So you have smaller gaps between allowed energy levels. So you have more ways of distributing the same energy, provided they have the same thermal energy. So you have to look, when you look at these things, you look at either increasing thermal energy, or you look at the situation where the thermal energy remains the same, and in those cases you just say, are we going into a situation where there is more freedom of movement for the atoms, less restrictions on the movement, then those would lead to higher entropy. Okay? And so if there's more freedom of movement, you say, we associate that with the notion of greater disorder. You might have encountered entropy in other courses, and you've been taught that it is a measure of disorder. That's actually only looking at one side of the picture. Okay, it's really a measure of how many ways you can distribute the thermal energy. And one way you can increase the ways of distributing the thermal energy is if you have more disorder, greater freedom of movement. Okay? So let's look at phase changes at constant temperature and pressure. Going from a solid to a liquid, like if you're melting ice, solid to liquid. What did we say entropy for that one? Does it increase or decrease? delta S was just delta H over T, right? And that's a positive number. We had that example earlier for heat, for the entropy of fusion of ice. Entropy increases. Why? As you're going from a solid water to liquid water, what happens? Atoms are more free to move in, the molecules are more free to move in the liquid. So that's a higher entropy. Liquid to gas, same thing, right? There's more freedom of movement in the gas than in the liquid. Solid to gas, that also increases entropy. So for all of this, delta S is positive. You have the same thermal energy, okay? All right? And so the energy you're putting in is used by the molecules to overcome the forces of attraction among them. So you have more freedom of movement, you get closer energy spacings, and you have higher entropy. What if you're looking at reactions? If you're asked to predict the delta S for the reaction, you're being asked to compare the entropy of the products versus the entropy of the reactants at the same temperature, okay? So what happens in a reaction? The more gas molecules or simpler molecules you're making in your product side, okay, then that means they'll have more freedom of movement, and you'll look at closer energy spacings that would lead to higher entropy. So let's take a look at a few questions here that illustrate these concepts. What's the entropy change for heating water from 25 degrees to 75 degrees? Is it positive or negative, A or B? Okay, this should be easy. Positive, right? Entropy increases. Delta S is positive. You have an ideal gas at 298 K1 atmosphere. Okay, you lower its pressure to half atmosphere at the same temperature. So same thermal energy. Okay, but you lower the pressure. What happens when you lower the pressure? Which law is applicable here? Boyle's law? P1 V1 equals P2 V2, right? At the same at constant temperature, pressure and volume are inversely proportional. So what happens if you lower the pressure? So if pressure goes down, according to Boyle's law, what happens to the volume? The volume goes up. So will the entropy A increase or B decrease for this process? Constant temperature. Okay, correct answer. Increase. Why increase? Volume expands. More room to move about. So greater disorder. Okay? Solid turning into a liquid, constant temperature. That's melting of ice. Delta S is positive or negative? Okay. Positive, right? Just talked about that. Next one. You have N2 plus 3H2 gives you 2NH3. Will this lead to an increase in entropy or a decrease in entropy? In other words, is delta S going to be positive or is it going to be negative? Constant temperature, looking at the same thermal energy for products and reactants. You're only going to compare this time the freedom of movement, right? The quantization of energy. Are you more restricted now or are you less restricted when you convert your nitrogen and H2 to NH3? Let's see. Negative. In fact, we calculated that earlier to be negative, right? So why is it negative? You have 4 moles of gas here versus 2 moles of gas. Okay? You have simpler molecules here. Your nitrogen and hydrogen are diatomic, whereas your molecule of ammonia is a polyatomic molecule. So there's more restrictions on the movements of the atoms in NH3. So from simpler molecules would be associated with higher entropy. So you go from simpler molecules to more complex molecules, that would lead to a drop in entropy. Okay? Entropy change for this, increase or decrease? Is it going to be positive entropy change or a negative entropy change? Calcium carbonate solid gives you calcium oxide solid plus CO2 gas. All right, answer, increase entropy, more freedom of movement here, okay, because of that gas that's formed. Okay, let's talk about spontaneity of reactions. Okay. At constant temperature and pressure, if you have a spontaneous reaction, what's our delta S? It's going to be the delta S for the system, and our system is going to be your reaction mixture, right? Plus the delta S of the surroundings. Well, delta S of the surroundings will just be the heat that comes in or out of your surroundings divided by the temperature of the surroundings, okay? So it's negative delta H over T. Okay, and delta H is the delta H for the reaction. If you look at this equation right here, okay, we can rearrange that, multiply both sides by T, so that becomes T delta S, and T will cancel here. And T times 0 is just still 0, so I have T delta S minus delta H must be greater than 0. Okay? Now, if I flip this around, okay, if I make both sides negative, take the negative of both sides, so negative T delta S and your delta H is positive right there. I have to flip this inequality right here. So this means that delta H minus T delta S must be less than 0 for a spontaneous process. Okay, let's understand that process right there. If I say X minus Y and Y minus X, how are those two related? I'm just taking the negative of X minus Y in order to get Y minus X, right? So if I say, okay, positive 5 is greater than 0, so if I take the negative of 5, how does that compare to 0? It's going to be less than 0. So you flip the inequality. So if T delta S minus delta H is greater than 0, then delta H minus T delta S will be less than 0. Okay? What this is telling you then is this. The spontaneity of a reaction depends on delta H and delta S. What's the nice thing about this? You're only looking at the reaction. You're not worrying about the surroundings anymore. Okay, we've replaced delta S surroundings with an expression that depends only on what's happening in the reaction. So this is a more useful expression for us. Okay, we prefer not to have to keep worrying about what's going on in the surroundings. So we just look at properties of the system or our reaction mixture. And so favorable conditions then for spontaneity would be an exothermic reaction. Why? We want delta H minus T delta S to be negative. So we want this to be negative minus, we want this to be a positive in order for the whole thing to become negative. Okay? So favorable conditions for spontaneity would mean a negative delta H, exothermic reactions. In fact, most of the spontaneous reactions you observe in nature are exothermic. They generate heat. Okay? And at the same time, another favorable condition would be a process that involves an increase in entropy. Okay? So if I were to ask you, if you were to put together all of these simple amino acids put together to build a protein, okay? A big molecule of protein, what would be the delta S for that one? Simpler molecules, building blocks, put them together to make something more complex. That would be a negative delta S. That's unfavorable, right? So there must be something else that would make it favorable. Okay, but it does happen, right? In certain cases. So you have to look at not just the entropy change. Okay, don't be misled into thinking that because delta S for building of a protein is negative, then it's not going to happen. You have to look at the overall picture. Okay, you have to look at delta H and delta S. Now, to make things even simpler, we can define a new property called Gibbs free energy. Gibbs energy is defined as H minus Ts. Okay. And the reason we define it is that if you calculate delta G, change in G, then that would be G final minus G initial, right? So that's H final plus Ts final minus H initial plus Ts initial. T initial, S initial. If you combine this H final minus H initial, that gives you your delta H, okay? And Ts final minus Ts initial, that will give you delta Ts. Now, we're generally going to be interested in processes happening at constant temperature. So if T is constant, delta Ts would just be Ts final minus Ts initial, where T final and T initial are the same. So I can factor that out. So that's T times S final minus S initial. So that's just T times delta S. So if you have a process happening at constant temperature, or if you want to look at two states of your system at the same temperature, okay, then the difference in the Gibbs energy would be equal to the difference in H minus T times the difference in entropy. Right? But what does this thing look like? We've seen this expression earlier. What is delta H minus T delta S? We've seen that earlier as our condition, as in our condition for spontaneity. For spontaneous process at constant temperature and pressure, delta H minus T delta S must be negative. That means delta H minus T delta S, that's delta G, right? So that means delta G, we say, if you have a spontaneous process, delta G, which is this expression right here, must be negative. What does it mean when we say that delta G must be negative during a spontaneous process? That means it must be dropping, right? It must be decreasing as the process occurs. Okay, so if I were to ask you, plot the Gibbs energy of a reaction as it's happening, what will you say? What will you do? If you could plot G versus the progress of a reaction as a reaction is occurring, what would G be doing? It will be dropping. Okay, eventually a reaction will stop, right? So that means you must have reached a point at equilibrium that the G could no longer drop. That means if it were to continue beyond that, the G would have to rise, right? So we say then that G is minimized at equilibrium. So this is where the Gibbs energy is minimized at constant temperature and pressure is where you've reached equilibrium. Okay, so this is the link between heat measurements, which you use to calculate delta H, determine delta H and delta S, and equilibrium. Two seemingly unrelated things are in fact related. Okay, and so the Gibbs free energy, the Gibbs energy, is your link between heat measurements and chemical equilibrium. So Gibbs energy is minimized at equilibrium. During a spontaneous process, the Gibbs energy of your system will be dropping. All right. So let's see how we can predict spontaneity for reactions. If you have a reaction that has a negative delta H and a positive delta S, okay, let's look at what happens. If delta H is negative and delta S is positive, what's a negative number minus a temperature, which is always positive, times a positive number? Negative minus positive is always going to be negative. So if you have a reaction that is exothermic, okay, with a positive delta S, it will always be spontaneous. What happens if it's the other way around? If you have an endothermic reaction, okay, delta H is positive, and delta S happens to be negative, it's the opposite, then delta G in that case will be positive. That reaction will be always non-spontaneous. Okay? Now, what about negative and negative? This is exothermic again. Okay, this one was endo. This is exothermic, but the entropy decreases. These are processes that tend to be spontaneous at lower temperature. Why is that? Let's look at our expression. Delta H minus T delta S, right? If delta H is negative and delta S happens to be negative, what did we say a negative delta H is? If you recall, a negative delta H is good, right? Why is negative delta H good? Because that gives heat to the surroundings. It makes the entropy of the surroundings go up. Okay? A negative delta S is bad, right? Why is it bad? Because you want the entropy of the universe to increase. You don't want, as much as possible, you don't want entropy to go down. But if the entropy of the system has to go down, we say your system is incurring an entropy debt to the universe. It has to make the entropy of the surroundings go up. Okay, that is why in this second case right here, if the entropy goes down, okay, you have to dump heat to the surroundings for the entropy of the universe to go up. But if you're absorbing heat from the surroundings, so these are two bad things. This is bad and bad, okay? So this is bad. You don't want entropy to go down, right? This is bad. You don't want entropy to go down. And exothermic is good. Okay, why is exothermic good? Because you're dumping heat to the surroundings, you're making the entropy of the surroundings go up. So that's good, that's good. So this is always spontaneous. This is bad. Two bads means won't happen, right? Always non-spontaneous. Exothermic is good, but if the entropy goes down as a result, what happens? You have to balance the good and the bad, right? So what happens at high temperature? Higher temperature favors the bad, right? So that means it's more likely to be spontaneous at low temperature. What happens if this thing goes to zero? Then it's just going to be good. The rest of it is good, right? So these are more spontaneous at lower temperature. So like turning from a gas, an example of this would be, what did I just do? Pressed the wrong button. Turning from a gas to a liquid. Gas to liquid. Okay, what happened here? Okay. Gas to liquid. What's the delta S for that? Positive or negative? Negative, right? It's negative entropy. Why? More freedom of movement in the gas, more restricted motion in the liquid. You say there's more order in the liquid, more disorder in the gas. So that's bad, right? To mitigate that, you lower the temperature because delta G is equal to delta H minus T delta S. So you minimize the effect of the bad by going to lower temperature. So condensation happens better at lower temperature than it does at higher temperature. Liquid to solid, same thing. Freezing is favored at low temperature, not at higher temperature, right? So that's why it snows in the winter when the temperature is colder. Liquid water turns to ice. It doesn't snow in the summer. Okay. Now, if delta S is positive, then that's good. But if delta H is positive, then that's bad. Okay. An example of this would be going from solid to liquid. Solid to liquid, that's an increase of entropy, right? But that doesn't mean it's going to be spontaneous, because why? Melting of ice, it's not always going to be spontaneous, right? It's spontaneous when you're in a hot environment, right? But if you put your ice in in the very cold freezer, it's not going to melt spontaneously. Right? So it's favored at higher temperature. Okay, what's the delta H for? What's the delta S for melting? It's positive, right? You go from solid to liquid. You have to, your system, your molecules need to absorb heat in order to free themselves from the forces of attraction that are holding them together. But at the same time, the entropy increases, okay? But at the same time, they're drawing heat from the surroundings. They're causing the entropy of the surroundings to go down. So you have to kind of balance two things. Let's look at this reaction here. Combustion of sugar. If sugar is burned, okay, do you think this reaction is going to be always spontaneous, always non-spontaneous? This will be spontaneous at higher temperature or spontaneous at lower temperature? Okay. Let me help you out here. What delta H do you think is this going to be? When sugar is burned, does it generate heat or absorb heat? When you burn something. So what's delta H? Negative. Is that good or bad? Good, because that gives heat to the surroundings. That increases the entropy of the surroundings. What's your delta S here? Look at the complexity of your molecules. Okay, positive or negative? So let's see. Is this going to be always spontaneous, always non-spontaneous? Spontaneous at a higher temperature, spontaneous at a lower temperature. Correct answer? It's always spontaneous, right? Delta S is positive, right? Simpler molecules here. So increase entropy, increase disorder. So delta A, positive entropy is good, right? So it's going to be always spontaneous. Now you may be asking, why doesn't, this is sugar, why doesn't sugar in your spoon, just take a spoon of sugar, why doesn't it just burn by itself? It's always spontaneous. Reactions require an activation energy. Once you get it going, then it will be spontaneous. Okay, some reactions do require a little activation for them just to get started. But once they get started, the process is spontaneous. And like I said, spontaneity and how fast things happen is different. It's different from how fast things happen. Okay. So things that are slow have a high activation energy. If you give them enough activation energy, then you can get them going. Decomposition reactions are generally endothermic. Okay, why is that? Let's look at the example here. Barium chloride dihydrate. If you want to decompose this, you're going to have to apply heat to this. So this is an endothermic process. So delta H here would be positive. Now, when you're decomposing, what's your delta S? So delta H is positive. Is that good or bad? As far as spontaneity is concerned. That's bad, right? Remember, delta H minus T delta S. You want that to be negative. So if that's positive, that's bad. What's delta S for this? Positive? Why? Going from this to this, simpler. If you're going to simpler molecules, you're looking at a positive delta S. So that's good, right? How do you emphasize the good over the bad? Ready? And when we say good or bad, it's just, I'm not making any moral judgments there, okay? It's just about whether it's good for spontaneity or not. So this is going to be spontaneous at higher temperature. The bigger your T value here, higher your temperature, the more you're favoring the good, your highlight, accentuating the good things, right? All right, so why is delta G, or G itself, called the free energy? Gibbs energy is also known as the Gibbs free energy. Let's illustrate that with this example. Let's say your delta H is negative 5 kilojoules. Is that good or bad? Good, it's negative, right? And let's say your T delta S is negative 2. Is that good or bad? That's bad. You don't want a negative delta S. But let's say that's your delta H and delta S. So delta G would be delta H minus T delta S. And that would be equal to what? Negative 5 minus negative 2. That would be negative 3, right? So delta G here is negative. So we expect this process to be spontaneous, right? So this is what we call exergonic reaction. Delta G negative is, we say, exergonic. What do you think a reaction that has a positive delta G is called? If it's not exergonic, it is endergonic, okay? Just like delta H is negative, it would be exothermic. Delta H is positive, would be endothermic. Okay. Now, because T delta S here is negative, this is bad, remember? So we say your process has incurred an entropy debt, right? So what does the system have to do in order to pay for that entropy debt? It has to release heat to the surroundings to compensate for that entropy debt. Since T delta S is negative 2, then it has to give up at least positive 2 to the surroundings. Okay? So it has to give up 2 kilojoules of heat to the surroundings to compensate for that entropy debt. Now, the process is a delta H of negative 5. That means for the process to occur, the system has to lose 5. It can lose up to 5 kilojoules of heat to the surroundings. Okay? What this is saying is this. Since delta G is only negative 3, it doesn't have to give up all of that 5 kilojoules as heat. It can use 3 kilojoules as work and only need 2 kilojoules as heat. Okay, so of the 5 that it has to lose, okay, 2 kilojoules must be released as heat to pay for the entropy debt. The remaining 3, it doesn't have to be released as heat. The system can use it to do useful things like push electrons through a wire and generate electricity and turn your motor and all that. Okay, so, or to move a muscle. Okay, so those are useful uses of more useful ways of using energy. Okay, so that's why it's called free energy. So it's only free to use 3 kilojoules out of the 5 in this particular example because the system has incurred an entropy debt. Okay. What if it's the other way around? Let's say delta H is negative 5, T delta S is positive 2. Negative 5, is that good for delta H? Okay. Positive 2 for T delta S, is that good or bad? Good, right? Okay. So does the system need to release heat to the surroundings? It doesn't need the surroundings. It could do things by itself, right? Because that would lead to an increase in the entropy of the universe. Okay. But how much is the system free to use to do useful work? Well, not only can it use that 5 kilo, doesn't have to dump heat to the surroundings. So that 5 kilojoules, it can use it to do useful work. In fact, it's allowed to borrow heat from the surroundings and convert it to useful work. So what's our delta G here? Minus 5 kilojoules minus T delta S, which is 2 kilojoules, negative 7 kilojoules. It's free to use up to 7 kilojoules to do work. Okay? By itself, it can produce 5. And it doesn't have to give it up as heat. It can use it to do work. But because delta S is positive, okay, it's rewarded by nature allowing it to take in 2 more kilojoules of heat from the surroundings and convert it to work. 2 more kilojoules of energy from the surroundings. Okay? So let's do a quick review. What type of processes are spontaneous at constant temperature and pressure? Endergonic, exergonic, endothermic, or exothermic? What's the condition for spontaneity? This is delta G positive, this is delta G negative, this is delta H positive, this is delta H negative, right? Which one is spontaneous? When delta G, oh, what happened there? When delta G is negative, right? Exergonic. Delta G negative, spontaneous process. Exothermic is good, but that's just half the picture, remember? You have to look at delta H and delta S together. And so it's really convenient to just look at delta G, because delta G is equal to delta H minus T delta S, right? So good would be exothermic and a positive delta S. That would lead to a negative delta G. Overall, you want a negative delta G. Okay. Gibbs energy and equilibrium. You can calculate the standard Gibbs energy of a reaction, okay, from thermodynamic table. So you can look it up. All you have to do is figure out delta H. We've learned how to do this earlier, right? Delta H for a reaction. And delta S for a reaction, we just covered that, right? So delta H minus T delta S would give you delta G. Or you can just look up what the standard Gibbs energy of formation of your products, and then subtract the standard Gibbs energy of formation of reactants. Delta G formation is defined in a manner similar to delta H formation. If you remember, we said delta H of a reaction is delta H formation of products minus delta H formation of reactants. Same definition for delta G of reactions. Okay? Now, why are we interested in delta G, the standard Gibbs energy of a reaction? Because that allows us to predict the equilibrium constant. So we can actually calculate KEQ for a reaction from the delta G for that reaction, the standard Gibbs energy for the reaction. Now, the Gibbs energy for an actual reaction mixture depends on what your reaction quotient is. Okay, so the delta G would be equal to the standard delta G, okay, plus RT times the natural log of your reaction quotient. And so what happens is, if your reaction quotient equals to KEQ, what happens? Then your delta G would approach zero. You'd reach equilibrium, okay? So delta G, the reaction Gibbs energy, is equal to zero at equilibrium. So that means, okay, you can say then that delta G, let me point that out here, is equal to delta G naught plus RTL and Q. So if this thing is zero, and then Q would be equal to KEQ. What do you get now? So you get 0 equals delta G naught for the reaction plus RT natural log of KEQ, which we can rearrange into this equation right here. So delta G naught for a reaction is just equal to negative RT natural log of KEQ, or you can use base 10 log for that. Okay? So if I know my KEQ, I can get delta G naught. What if I knew delta G naught? How do I solve for my KEQ? I divide both sides by negative RT. So delta G naught over RT, negative, equals ln of KEQ. And then I can just solve for KEQ. Okay? KEQ equals e to the negative delta G naught over RT. So where can you find delta G naught? You can look it up from the web book or at NIST, or you can look at the back of your book. So let's go back to that web book.nist.gov. Let's say I wanted to do NH3, okay, gas phase. Do a search, ammonia. You'll see here, there's no delta G naught here. It doesn't have that. It has delta H and S. But if you can calculate delta H and delta S, that should allow you to calculate delta G. Okay? So let's apply that. Let's say you found your delta G naught, standard Gibbs energy of your reaction, to be 300 kilojoules. What would be your KEQ? What's our formula? KEQ equals E to the negative delta G naught over RT. That's going to be equal to what? E to the negative 300 times 10 to the third joules. Okay. Okay, that's per mole of reaction. Okay. It has to be in reference to a reaction, so let's call that per mole. R is 8.314 joules per Kelvin per mole. And our temperature is, what's our temperature? Unless otherwise specified, we're going to assume 298 Kelvin. Right, so Kelvin cancels out, moles cancel out, joules cancel out. That's a unitless quantity. So what would that be? 300 times 1,000 divided by 8.314 divided by 298. That's e to the negative 121. Okay? And what is e to the negative 121? I make that negative. Inverse log. So inverse log, that's e to the x. That is 2.6 times 10 to the negative 2.6 times 10 to the negative 53. What does a very small KEQ value like this mean? At equilibrium, how far has the reaction gone? Hardly, right? It's hardly gone forward. Most of the reactants are still there. They're very, very, very small trace amounts of products formed. That's a very small KEQ. Is that consistent with our notion of delta G being non-spontaneous if it's positive? This is a very positive number, right? A very positive number means you're going to have a very small KEQ. Remember, you want exergonic reactions, and those are the spontaneous reactions. So this reaction is not going to go very far. What would it be if it's the other way around? If this was negative, if it was the other way around, if it was e to the positive 121, what would it be? 121 inverse e to the x would be 3.5 times 10 to the 52. Okay, so if delta G was negative, 300 kilojoules per mole, then you're going to get a KEQ, which is very large. It's going to go all the way to the product side. Okay, so a negative delta G means reaction KEQ is going to be large. You're favoring the product. A positive delta G means you're favoring the reactants at equilibrium. So, check which reaction has a larger KEQ. Reaction with delta G naught of plus 30 kilojoules, one with the negative 30 kilojoules. Is it A or B? More negative delta G, farther the reaction goes, the larger the KEQ. And let's calculate delta G and Kp for this reaction. Well, we calculated delta S for this earlier. What was it? Let's calculate delta H and delta G since I don't have access to Gibbs energy delta G of formation. Let's look at delta H and delta S for this. Okay, delta H for this reaction would be 1. Delta H formation of NH3 minus, oops, this should be a 2 right there, okay? So 2 times minus delta H formation of N2 plus delta H formation of H2. What are these numbers? Let's look it up. NH3 delta H formation of NH3 gas is negative 45.9 kilojoules per mole. This was NH3, huh? Yeah. So negative 45.9 kilojoules per mole. How many moles of ammonia do I have here? 2. Okay. Times 2 moles. Okay. 2 moles ammonia per mole of reaction. Okay. Minus, what's the delta H formation of N2? It's going to be 1 mole N2 times, do I even need to look up delta H formation of N2? Element in its standard state, so that's going to be 0, right? Plus 3 moles of O2. What's the delta H formation of O2? H2. Again, H2, you don't need to look it up. It's going to be 0. So what is this number? 2 times negative 45.9. Negative 91.8 kilojoules. Okay? What's our delta S? We did this earlier. Well, you remember what our delta S was? Let's go back. Here. We calculated delta S to be negative 198.11 joules per Kelvin. Remember that? 198.11 negative. Okay. Oops. So negative 198.11 joules per Kelvin. Be very careful when you're combining your delta H and delta S. Delta H values are generally tabulated in kilojoules per mole, whereas delta S values are tabulated in joules per Kelvin per mole. So what's our delta G of our reaction? It's going to be delta H minus T delta S. What's our delta H? Okay, did I have the right balance equation when we did the delta H before? I hope I did. Yeah, I did have 2. Okay, so I did have it balanced. Okay, so what's our delta S? Delta H is negative 91.8 kilojoules. So I'm going to change that to joules. Okay. I'm just going to keep it kilojoules. Okay, minus, what's our temperature? Unless otherwise specified, we're dealing with 298 Kelvin times negative 198.11 joules per Kelvin. Okay. And one of these I have to convert to the other unit. What unit should I be converting? I want to make this kilojoules, so that is 298 times 198, that's 59,000 joules. So that's 59 kilojoules. Okay, negative, negative, so that's positive. 59 kilojoules. 59.0. And this is negative 91.8 kilojoules. Okay. So our standard Gibbs energy is, so that's divided by 1,000. That gives it in kilojoules. Add that to negative 91.8. That gives you negative 32.8 kilojoules. Right? How do I calculate Kp from that one? Kp is equal to e to the negative delta G naught over RT. Same type of calculation we did earlier. Okay? And that should be it.